Tetrahedrons are just awesome. Let me show you why. Let's add a little box here. That's a box. And let's add a cylinder to go right next to it, right there. And you can see these are two figures where they have not been joined yet. So let me merge them. I'll merge them with a Boolean union. So select this volume, E, this volume. And now the figure is merged. It's one single geometry. And I can go ahead and just simply mesh this. This is wonderful. So tetrahedrons are great at meshing complex geometries. There are very robust algorithms for meshing with tetrahedrons. In this case, these little pyramid-like shapes, they have 4 nodes per element. And I can go ahead here in Gmsh and set the element order to order 2. So the element order to the number 2 and remesh. And you'll see we're generating now second order tetrahedron. And what that gains you is the ability to match curved surfaces nicely. And it also is going to give you some benefits when it comes to convergence of your finite element method. This is what we're going to be talking about in this more theoretical video, all about tetrahedrons. Hi, I'm Jose, civil engineer. And in this video, we're going to be using this little geometry example of a cantilever beam being subjected to its self-weight as discretized with tetrahedrons. And we're going to see how the tip displacement depends on the meshing, that is the amount of elements that you have, the discretization size, as well as the order of the mesh, how those two things affect the convergence of your finite element method. Before that, I'd like to invite you to like and subscribe to this channel, and also leave a comment below. Tell me your favorite flavor of cookie if you want. But there's also going to be some code in this video that I'm not going to completely discuss. So if there's a question you have regarding the code, then feel free to ask a question. I'll be happy to respond in the comments. You're going to need the latest version of my Gmsh OpenSees translator for this tutorial. So make sure you're up to date with that. And you'll find everything that you need for this video in the description of this video. So without further ado, let's go and see some discretization effects on finite element convergence. So first, let's start with our geometry. The geometry is very simple. I have a box that has 30 centimeters wide and 60 centimeters tall, and it's 4 meters long. And I'm creating 3 physical groups that I'll show you right away. Here's the little box. I can mesh this with tetrahedrons by pressing the number 3 key right there. And the fixed portion is the surface physical group at here where I want to put the fixed boundary condition. And then I have a solid group, which is this area inside. And then I have a point, which is the tip right there, that I want to record the displacements. So here in Gmsh, you can control the discretization size. With the general, you can set this element size factor to something small and press 3 again, and then you get a new mesh which is smaller, like this. Let's enable visibility of the nodes for a second, and let's change the aspect to a sphere, which makes it a little bit clearer. And then here I can switch the element order to 2 by setting that and remeshing, and you can see that you get a finer mesh. Now, we want to be able to compare meshes that have the same amount of nodes. So in order to do that, we need to do a little trick. So let's go back to element size factor of 1. Let's press 1 there, and that's a mesh size factor of 1. So if I see the number of nodes that I have in statistics, 479 nodes. And if I go to a first order mesh, I don't get the same amount of nodes. I get less nodes because the way the high order mesh works, it inserts nodes in the mid sizes there. So let's see the statistics. I have only 92 nodes, but here's the trick I'm going to do. If I go to mesh and I say refine by splitting, I add more nodes. So I split the tetrahedrons, but now if I update, I get the exact same amount of nodes as in the second order mesh. So I'm going to be comparing a mesh that has been meshed with single order elements and then refined with an unrefined second order mesh. So let's do that again. Let's go to order 2. If I go here and, I set the element size factor to 12. There we go. We have 479 nodes. So that's the way you switch between the 2 types of mesh. Now we're going to be doing this from Python. So that's going to be something different. We're going to be controlling the discretization of the mesh. from Python, and that's nice if you want to have more control over your simulation, do some adaptive meshing and some other things. So let's take a look at the finite element side of this. OpenSees provides two tetrahedral elements. You can see to your left the 4-node tetrahedron element, so right about over there, and up here is the 10-node tetrahedron element. You can see the commands. The difference between the two is obviously the amount of nodes, 4 nodes for the 4-node tetrahedron and 10 nodes for the other one. So you're going to need to specify that. But the other main difference is the number of Gauss points where the material is integrated. For the 4-node tetrahedron, you just need 1 Gauss point, because those elements, and this is going to be important, those elements assume that inside the element, the strain field is constant. So they're also called constant strain tetrahedrons, or constant stress, because if the strain is constant, then the stress is also assumed constant. The 10-node tetrahedron, on the other hand, inside, because it uses a second order interpolation from the nodes, then you get a linear order interpolation of the strains inside the displacement. So this is also called the linear strain tetrahedron, or the linear stress tetrahedron. But in order to integrate a linear function, we're going to need those 4 Gauss points which are there. So main difference between the two elements, 4 nodes versus 10 nodes, 1 Gauss point versus 4 Gauss points. And this is going to have a huge impact in convergence and the amount of computational work that we're going to do, as we're going to discuss now. Let's take a look at what the Python code for the finite element model looks like. Okay, so here we have example6.py, the Python script for this analysis, which is available in the video description. We import OpenSees as OPS. This might be different than Windows, Mac. This line might be different in your code. Gmsh to OpenSees, my Python module for interfacing Gmsh with OpenSees, imported as G2O, Gmsh and NumPy. And then the first thing we do, we initialize Gmsh and we load the geo file. This is different from previous videos. We're importing the geometry in this case because we want to control the meshing from the script, which is going to be a great advantage for this convergence study. Next up, I have a series of parameters here. I'm going to set this one to false. So I'm going to set this one over here to false. So that we're going to pick the order, the mesh size, whether we want to show the mesh. I'm going to set that to true for now. Show results and write results to do the convergence study. Next thing is how do we set the mesh size? Well, we call this Gmsh option set number function with the mesh size factor. That has the same role as the number I was changing in the GUI before. And we give it this mesh size factor. We're going to leave it at 1 at this point, and we're going to be changing the denominator of this function to make it smaller. Next up, we have 2 options. So in the GUI I showed you that in the case of the order 1 elements, we're setting the mesh order option, element order option to 1. We're generating the mesh and then we're refining. And the reason for that was to have the same number of nodes, whether we're talking about the first order option or the second order option. In the second order option, we set the element order to 2. We generate the mesh. And here I'm setting up a variable in each case to count the number of Gauss points, total number of Gauss points I have in the mesh. This is going to be important in our discussion moving forward. Next up, what do we have? We initialize OpenSees with 3 dimensions and 3 degrees of freedom per node. That is standard. We're generating a new material model that is for steel, assuming steel. This is a very large steel beam, by the way, very heavy. Not realistic, but it's okay for our discussion. And then we're going to get the information of the elements that belong to the solid physical group. So we're going to be interested in these element tags and the node tags. Then I'm going to build some arrays, count the number of nodes, count the number of elements in the mesh, and the number of degrees of freedom are going to be 3 times the number of nodes. That's important for our benchmarking purposes. And the number of Gauss points is that variable that I defined previously, times the number of elements. And I'm going to print out to the screen. So if I execute this script, what I get is basically the visualization of the mesh with the options I have. So I want to take a look here maybe at the kind of mesh that we're building. In this case, it's a standard tetrahedron mesh. And I want to check whether if I change here to 2, if I get a finer mesh, that's all working. You can see the mesh is much finer in this case. And then if I switch back to first order, so the first discretization and order 2, I want to check whether I'm getting a second order mesh. To do that, enable element faces and nodes. Nodes will give you the information. So you can see those purple dots in the middle are the high order nodes for the high order mesh. So let's set the settings back to standard. We're gonna set that flag to false and move on. We're gonna set the next flag to true. So we're gonna wanna be able to see the results. What comes next? Next, add all the nodes to OpenSees. So read all the nodes from the mesh and add to OpenSees. And next, after that, we add the elements. Now, the elements, the logic is the same as in the previous videos. Smart lighting came off. In the previous videos, if the order is 1, I'm adding a 4-node tetrahedron, and if the order is 2, I'm adding the 10-node tetrahedron. And you can see, because the syntax of both commands is the same, and I'm using this fancy star, this is called the extract, no, I don't remember what it's called, but anyway, the syntax is the same, so the commands look pretty much the same. I could probably simplify this Python code to be a bit smarter, but that's good enough for today. Then next, I'm getting all the nodes that belong to the physical group called fixed. This is going to be our fixed side of the cantilever beam. And you can see here I'm using these underscores to just ignore the other output variables. And I'm just focusing on the node tags. And with the node tags, I'm calling the Gmsh OpenSees fixed nodes function with all the DOFs. The same now for the tip node. I'm going to extract the tag of the tip node. That's very standard. And then I'm going to be loading. So in order to load the model, a constant time series, a plain load pattern, and all the tetrahedron element tags that I got from the first, over here, there they are. That's that variable that's going there. I'm going to add all those node tags, element tags, sorry, and be loading them with self-weight in the Z direction. Standard analysis options for a static analysis, and then after that the analysis is done, I can retrieve the tip displacement and we're going to report it to the screen. Other than that, what I'm doing here is I have an option to write the results into a text file. That's nice for trying different mesh sizes and comparing. I'm going to show you the results of that later. I already ran the benchmark. And then if show results, I'm going to be showing stresses in the tetrahedron elements. This is code you should be able to run right now as is. For the order 2 mesh, you need the nodal stresses variable, and this is not something that is available in current OpenSees. If you want the version of OpenSees that can do this, you're going to be needing to compile your own version of OpenSees starting from my repo. I'm going to give some instructions on how to do that in the description below. And anyway, we add all those views to Gmsh, and these options are in the previous videos. Take a look at those if you want to see what this means, or ask in the comment section, and finalize. So after that, we can run this for this first case, and you can see here by default the post-processing views I'm showing is the first one. This is the stress in the X direction for the beam, and you can see there's negative numbers, compression down here and tension up here, and I can deform this mesh. Let's say here, so transformation, I can use a general transformation and use view number 6. That's the deformation, and I can apply a scale factor here, so something like 10 to the 3 maybe starts showing some deformation. 10 to 4 is too much, so 10 to 3, like maybe 3 times 10 to 3, something like that. And you can add the element outlines and it looks a bit cuter, and Alt-M to remove the mesh. So that's the deformed shape. The tip displacement is shown over here in the screen output. I'm getting like 00029, you can see there. So now with this script, we can easily control the discretization from the Python script. So I can go here now and set the discretization to half the previous size, rerun the script like this, and you see there's way more elements, and I can do the same trick as before. Let's go into options, transformation, use general, and view number 6. This can all be automated. I need something like 3000, I think. Yeah, that's the right size. We can also see the displacement is bigger now, 0.0034. It used to be 29, and now it's 34. The reason for that is that finite elements are always stiffer than the equation they're representing. So you're going to get a stiffer result than what you expect from the mathematical model that you have, right? As I increase the discretization, this should take more time, and this displacement should converge to a larger value. Let's try one more. Let's go to 10 to 1/4 of the original size. Here we can see that it takes a little bit more. OpenSees is struggling a little bit. And there we go. And as before, oops, I clicked on the wrong thing. And it's out of screen. Oops, sorry about that. Here we go, options, transform, and set to this, and 3000. You're not going to see the difference here, but you can see the stresses get resolved a little bit better. Let's turn off the mesh. And we're now at 35 times 10 to the minus 4, I guess. And compression at the bottom, tension at the top. This looks nice. This looks okay. And if you can see here, there are jumps in the stresses. This is that because within each element I mentioned, the stress is assumed to be constant. So each of these can only be colored like this. Now, a cool trick for visualization, and it actually improves the quality of the stresses, is to, at this point, apply the plugin, go to plugin, and you can apply smoothing here. So you can go and say, okay, let's smooth view number 0, and there you go. That looks smooth, and that stress prediction is a bit better than the one that comes right off the bat from the elements. So it's a worth thing to do. And I kind of like when the stresses are presented in this way. This tends to look nice and it gives you nice ISO values. Okay, so let's move now to a second order mesh. So second order mesh, and I'm going to go to 1 over here and visualize that. What does that look like? So it looks not too different from the before, but you can see it's less elements. It looks like less elements. Let's deform this, general transformation, view 6 and 3000, like this. And the displacement actually predicted at this point is 36. So we're at a better displacement prediction at this scale than the previous mesh. So that's going to be important. The other important thing to note here is that the number of Gauss points, 820, is less than the one we had before. I don't know if the history is here all the way from the beginning. Maybe here. Yeah, we're going to need to run the other one again. But you can see the number of Gauss points is 205. Sorry, here it is. 820 on the Gauss points, 478 on the number of nodes, and I'm getting a better prediction. Let me show you again. So if I go back to first order for this same mesh, discretization size, I get a really bad prediction, 29, and I have about double the number of Gauss points. If you're using a nonlinear material, that's really important because at each Gauss point, the constitutive, for example, plasticity computations, which are highly nonlinear, highly iterative, that's where they occur, and the more Gauss points that you have, it's going to spend more time there. So if you're doing nonlinear, you're going to want less Gauss points, and second order meshes actually get you that. So the other thing I can note from the second order mesh is the linear stress change that I showed you, that I talked to you theoretically. You can see each element is not quite a single color. There's shades to them, and that's because within each of these elements, the variation of the stresses is linear. Again, to visualize this, you need the newest version of both the OpenSees and the Gmsh code to do that. If you don't have the newest version of OpenSees, you can turn that off, and you can use this other visualization option, which will actually use the stress average. So it's going to look like there's no change in color, but it's actually, it is inside. You're just showing an average value for the stress prediction. So what happens if we plot everything together? So if I want to see, I prepared this plot, I changed, let me show it in this way first. So in the vertical axis, I have the tip displacement in millimeters, and the number of nodes in the x-axis, and you can see the blue line is this first order solution, and the orange line is the second order solution. And you can see right off the bat that the second order mesh pretty much converges. I would say it's converged at this point. So convergence for me in this case means that going from one number of nodes to doubling the number of nodes doesn't get you a big difference in displacement. That's what you see here. Whereas in the blue line, you can see that doubling the number of nodes actually has still not converged. I'm not seeing a plateau here in this line. So I'd like to see a plateau, and keep the last point before the plateau. So in this case, my converged mesh will look like this. Now the vertical scale is it's not starting at 0. So if you want to see realistic values, this is what they look like. That's 0. So they're still a bit far away. So that might be a percent difference. Maybe that's 80% of this value. So you're 20% off in this solution over here. So second order meshes actually get you a bunch of things. They get you faster convergence for the same number of nodes. You get better solution right away with less Gauss points. So that means you're doing less computation. What you do get is an increased bandwidth of the stiffness matrix, but that's not really a big deal. You can live with that because that means more computational expense in inverting the matrix. But of course, that's well paid off by your other gains. So what I mean that is that for the same number of nodes, the second order stiffness matrix is going to be larger, have more components than the first order one. So it's going to be harder for the system of equations to actually solve it. But that's not really a big issue. It's something you can handle, because with the second order mesh, you can go with less nodes than with the first order mesh. So at this point, I just want to invite you to like the video again. If you like this content, if you were interested in seeing something else, let me know in the comment section below. Remember, everything is down there in the video description, and ask if you need any help. I'll be happy to talk to you in some way or another. See you guys next time.